So far we have been studying addition, and we did not discuss how we do subtraction. Subtraction is actually performed by the same circuit that performs addition in a computer, because subtracting a number from another number is equivalent to adding the negative of the number. So if I have the operation 7 minus 6, I actually going to perform the operation 7 plus minus 6. So if I have plus 7 and I want to add, I want to subtract 6 from it, I actually will gonna add minus 6 to the result, and you see the operation here that will result in this case into the value plus 1. So the question is, how do I detect overflow in a subtraction? So plus 7 plus minus 6 is equal plus 1. So subtraction overflows if the results are out of range. And in the case of A minus B, what I have is that if both of them are positive, then I cannot have overflow, because subtracting two positive numbers, the module of the result must be smaller than the module of the two operands. Same thing if I subtract two negative numbers, the module of the result has to be smaller than the operands. The only situation where I can have overflow is if I do A minus B. If A is negative and B is positive, then the result has to be negative. So if I got a positive result, then I got overflow. And the other situation is if I have A minus B and A is positive and B is negative, then if I get a negative number, that must be an overflow. So those are the only four possibilities. So we have discussed the possibility that when I do an operation, whether it's an addition or a subtraction in a computer, I can result with end up with a number that I cannot represent in that representation. For example, in the 32-bit architecture, the result cannot be represented in 32 bits. How do I handle overflow? So depends on the programming language that you have. Some languages simply ignore overflow. For example, C tells you that you don't need to worry with overflow. You never check for overflow. So in this case, you use the RISC-V add, I, or sub instruction where there are no checks. In other languages such as Ada and Fortran, you must raise an exception if an operation results in overflow. So in that case, in the MIPS architecture, we had instructions that would raise an exception if there was overflow. In RISC, we don't have that, and RISC has no special instruction support for overflow. That should be done on integer operation. So you also gonna use add, I, and sub instructions, but then what you're gonna do, you're gonna code the check yourself. So if your language requires you to check for overflow, you're gonna have to insert code in your assembly program, or your compiler gonna have to do that to check for overflow. And if there is overflow, then you're going to throw an exception and invoke the exception handler. I know that we have not discussed the exception handler yet, but soon we're going to be discussing the exception handler in 229. And the exception handler will save the current program counter in a special register called the user exception program counter, and then we'll jump to a handler that the address of a handler that is a special program, and this address is stored in a register called the user trap handler base address, that is the UTVEC. Those things, the exception program counter and the user trap handler base address, will become clear in just next week when we're going to be talking about exception handling in RISC-V. So for dealing with overflow, what the risk designers did is to provide you with examples of the types of instructions that you can insert in your code to check for overflow. If you have an unsigned addition, then you're going to have an overflow if the result that you get is less than either one of the operands. So you just have to check against one of the operands. If you got a result that is smaller than the operand, then you must have had overflow. For a signed addition, when one of the operand signs is known, so if you have an immediate and the immediate is positive, for example, so you have an add I with a positive immediate, then you're gonna have an overflow if the result that you got is less than the value that was in the register. So you add T1 with a positive immediate, the result that you got cannot be less than the value of T1. If you, in the signed case, that's the general case where you do an addition of the value of two registers. So you say A is equal B plus C. In that case, to check for overflow, first you're gonna check whether T2 is negative, right? So you set the value of T3 to 1 if the value of C is negative. So you check the value of that operand. Then you're gonna check to see whether the result that you got is less than the other operand. So you are asking whether A is less than B. So if those two values, so if C is negative, then A has to be less than B. And if C is positive, A cannot be less than B. That's the logic here. So if you look into what's happening here is, the first test is to say if C is negative, then A has to be less than B. Or if C is not negative, A cannot be less than B. So those two values, they either have to be both 1 or they have to be both zeros. So whenever your architecture requires you, or your language requires you to check for overflow in every instruction, every addition that you do in your code, for example, would have to be followed by these three instructions, where the last instruction is a branch that sends you to a place where you're going to throw an exception, and the exception handler will be invoked to handle the overflow. So that's what we had for overflow. Handling overflow in RISC-V does not, you don't have hardware support for that, and you have to insert the proper instructions to handle overflow in your assembly code. Now let's look at arithmetic for multimedia. We often are using our processors to process graphics and media. And when we are doing this kind of processing, we are operating data that is smaller than 32 bits. So often we are operating 8-bit or 16-bit data. And in that case, I would like to be able to partition a word into smaller pieces, right? So for example, if I have a 64-bit architecture, I can partition the adder, that addition that I do, in what is called a partition carry chain. So all I need to do to make an adder that was previously a 64-bit adder to become 8-bit adders is to cut the carry chain every 8 bits or every 16 bits or every 32 bits. So the idea here is that all I need to do is to not propagate the carry at certain spaces in the adder. And that will allow me to, for example, load 8-bit values into a register and do an operation and then obtain the results without the carry. For example, these 8-bit values could be processing a stream of sound, for example, or the 16 bits could be pixels in images, etc. So what we want to do is to do a mode of operation that we call single instruction multiple data. So I did, for example, my addition, and those 64 bits represented, for example, 8 items of data that are different, separate from each other. And I did all those operations in one cycle. And that's why we call it single instruction and multiple data. And in multimedia also, often I want what's called saturating operations. So if there is an overflow, I don't want the result to be the next value. I want it to saturate at the maximum. This is very common for example, clipping the sound signal. I don't want it to, when I add 1 to the highest value, I don't want it to go around to 0. I want it to stay at the maximum sound, for example, that I can represent in an audio signal. So if there is overflow, the result should be the largest that's representable in the value. And as I said, the examples of that would be clipping in audio or saturation of color, for example, in video. So this ends our lecture on addition and subtraction. One of the things that we did not mention in this lecture, but I think it's worthwhile mentioning, is that to perform the subtraction using the same circuit as the adder, all I have to do is to flip all the bits of the second operand and then make the carry in, the carrying of the bit 0 equal 1. Because if you think about that, that's exactly what we do when we are converting a number to its negative representation, right? We flip all the bits and you add 1. So we can do that with the same circuit by simply flipping. If I'm doing a minus b instead of a plus b, all I have to do is to flip all the bits b and add 1 with the smallest carry. So that's how subtraction is implemented in a computer.